to try to get a feeling for what the second order partial derivatives of a function mean, let's see if we can figure out the sign of each of these partial derivatives just based on this contour plot. So it's maybe a little hard to read on this contour plot all of these contour labels. They're all negative numbers. The only ones that are positive are the 0 contours here. Okay, and actually this contour plot is a little misleading because actually there is one contour that's missing that I should have included in the picture. That's right down the middle here. This contour, let's say that it's 1. Okay. So let's figure out at this point here, right in the middle, are each of these derivatives positive or negative? Okay, now these first two, these are just the first partial derivatives in each direction. So we've looked at examples of how to approximate these based on a contour plot. So going in the x direction, like this, we're actually at a high spot, right? Because to the left of us is the 0 contour, to the right of us is the 0 contour, and we are on the 1 contour. And so that means we're on a high spot moving in the x direction. And for a high spot, the slope of the tangent line is 0. So it seems like this one actually isn't positive or negative, it's 0. Okay, now let's look in the y direction. Same thing happens in the y direction, right? So below us in the negative y direction is the 0 contour. Above us in the positive y direction is the 0 contour. We are on the 1 contour. And so that means we're on a high spot moving in the x direction, and that means this partial is 0. Okay, those were the easy ones. So now let's think about the second order partials. Notice I've only listed 3 of them, and that's because the one that I'm missing, which is partial squared f partial y partial x, is equal to the other mixed partial by Clairaut's theorem. Okay, so let's work out these second order partials. So for partial squared f partial x squared, we have to imagine what is happening. So remember, this is the derivative in the x direction of partial f partial x. So we have to imagine what is happening to partial f partial x as we move in the x direction. That is a little hard to picture just based on the contour plot. So what I think the better thing to do is to use the contour plot to come up with at least near this point, come up with a mental picture of what the graph looks like, and then manipulate that picture. So what is happening on this graph? Well, this diagonal ridge line at height 1, right? It's this high ridge going from the upper left to the lower right. The upper right is low because all these contours are negative, in fact, very negative. And to the lower left, these are all low contours because they're all very negative as well. So we have this diagonal ridge line with a low spot to the upper right and the lower left. Okay, so it's as if we took a square piece of paper here, but then curved the upper right corner and the lower right corner downwards. That's going to look something like this. So hopefully this is what your mental picture gave you. Can I turn this? I should be able to turn this. Okay, right. So if we look at it from above, right, there's our diagonal ridge line, and then the upper right and the lower left are curved downwards. Okay. All right, so what we're going to do is first imagine for the second partial in the x direction, remember we're going to look at the slope of the tangent line in the x direction, so that's partial f partial x, and then think as we move in the x direction, is that positive or negative? Okay, so let me hide the tangent line in the y direction so we can concentrate on the thing we care about. Okay, so we're starting to the left of our central point and we're moving in the x direction and watching what happens to the slope of the tangent line, so like that. So let me back up again. Okay, so to the left of our starting point, the tangent line has positive slope. And then as we move rightwards, the slope goes to 0, and then it goes negative. So the slope of this line is positive, 0, then negative as we move in the x direction. So that means the slope is decreasing, and that means this derivative is negative because this slope, partial f partial x, is decreasing in the x direction. Okay, so now let's look at partial squared f partial y squared. So this is going to be the same idea, but in the y direction instead. So let me hide the x direction and show the y direction. This is a little hard to see, so I'm going to turn the picture so we can see that y direction. Okay, so now we're going to start at our top point, which is right here, which, right, if we sort of get a different perspective, that top point, the tangent line is horizontal. Okay. So we're going to start to the negative y side of that point and then move in the y direction to the positive y side of that point, like this. So on the negative y side of that point, the tangent line has positive slope. And then as we move in the y direction, that positive slope becomes a 0 slope. Remember, this is horizontal there. And then as we keep moving in the positive y direction, I've lost the ability to move that point. As we keep moving in the positive y direction, that slope becomes negative. Okay? So as we move from the negative y side of our target point to the target point to the positive y side of the target point, our slopes are going from positive to 0 to negative, and so this derivative is negative. And again, this is because, right, we were measuring the rate of change in the y direction of partial f partial y. Partial f partial y, that is the slopes we were looking at, and these were decreasing as we moved in the y direction, and so this whole thing is negative. All right, so now let's look at the mixed partial, partial squared f partial x partial y. It's kind of a mouthful. Okay, so this is the partial derivative in the x direction of partial f partial y. So we're going to look at our slopes in the y direction, but we're going to move in the x direction. Okay, so since we want the slopes of the tangent lines in the y direction, those are the tangent lines that we have plotted right now, so we're going to keep this tangent line. But instead of moving in the y direction like this, we're going to, from our target point here, we're going to move in the x direction like this. Okay, like this. Okay, so starting at our target point, this slope is 0, right? Because it's horizontal. If we start to the negative x side of our target point, the slope of this line is positive. If we slide over to the positive x side of our target point, this tangent line has negative slope. So as we move from the negative to positive x side of our target point, our slopes go from positive to 0 to negative. And so this slope, partial f partial y, is decreasing, and so this derivative is also negative. In fact, all of these are negatives. Because of Clairaut's theorem, we know that partial squared f partial y partial x is also going to be negative, but let's check on that just to make sure we understand how it works. So this is going to be the derivative in the y direction of partial f partial x. So partial f partial x, these are going to be the slopes of tangent lines going in the x direction. So let's hide our tangent line going in the y direction,